the current slide. And the only announcements I know, the volleyball team is in Boaz. If they're not there now, they're on their way for the national, the district tournament. And I hope they do quite well. They're a very good team. And that's today, tomorrow, and Sunday. So if you can get up to Boaz and cheer them on the victory, I think that Sneed State Community College is probably where the tournament is being held. Now there's also this thing, and since I know two people are here, but I don't know if I've announced this before. There was a postdoc at UAB, there is a postdoc at UAB who sent Dr. Wilson this notice that, I think I announced it in here, there's a 1-week special thing this summer for students who are interested in biopharma manufacturing as a career. Okay, 1 week they're hosting you somewhere. You can go to the website and find it out. She didn't indicate anything in that except the link to the website. And they will pay you $1,000 for that week and cover your travel expenses. So 1 week out of the summer, whoa, and you get paid for it at a pretty good rate too. So if you're interested in that, I've got the thing on the desk in my the classroom I usually teach from. I'll be glad to share that website with you. I don't know any more detail. All she said other than that was the deadline is in January. She didn't say when in January, sometime in January. So anyway, get the information before January if you're interested and start the process for applying. All right, any questions on anything we've done up till now? Okay, just a little bit of a reminder. We're trying to find zeros of a polynomial function. Everything we've done up till now basically has led to this. We've done it for quadratics, but what about these higher order polynomial functions? We've done it for linear. Those are pretty easy. Okay, but how about these? Well, the first test that we use to try to find those zeros is the rational zero test. Now, this won't find them all, but it has potential to find any rational zeros. And here's what the rational zeros test is. It relates the possible rational zeros of a polynomial. Now, these polynomials must have integer coefficients. If the coefficients of those terms in the polynomial are fractions, decimals, rational or irrational numbers, rational zero test will not work, okay? But if those have integer coefficients, I think just about everyone we've had so far has had integer coefficients. So, you may think of a couple that haven't, but if most of them do, if they do have this, then what we do is use just that leading coefficient. Boy, we've used that before, haven't we? And the constant term at the end. So the term at the beginning, the coefficient at the beginning, and the term at the end, we'll use those two to determine potential rational zeros. So here's what it is. So here's your polynomial function. F of x is equal a sub n, x to the n, a sub n minus 1, x to the n minus 1, blah, 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 a squared, a sub 2, x squared plus a sub 1, x to the first plus a 0. If every one of these a's, now remember this subscript here means nothing except this is the a that goes with that exponent. The exponents mean something, okay? The subscripts just say we're the ones that goes with that one, okay? And remember, for this to be a polynomial of degree n, that a sub n can't be 0. Okay, it cannot be 0, otherwise it would be a polynomial of degree a sub n minus 1, and then we would deal with that one. So the leading coefficient can't be 0. Okay, now all these a sub n's have to be integers. Again, no fractions, no decimal, no rational, no irrational, certainly no complex, okay, just integers. Then every rational zero that this function has will be of the form p over q, a rational zero, okay? Now where does the p come from? P and q have no common factors. If they have common factors, other than one, of course, if one's a factor of everything, no common factors, okay? They do have common factors, you have some problems there. But if they have no common factors, and what the P is, that numerator, is a factor of the constant term. Now this is a lot of blah, blah, blah right now, but when we do some examples, it will start making, hopefully, a little more sense. Q, the denominator, is a factor of the leading coefficient. That's why, another reason, a sub n can't be 0. Certainly 0 is not a factor of it, okay? So Q could be a factor, it is a factor of the leading coefficient, a sub n. All right. Again, a fair amount of blah, blah, blah. Excuse me. To use the rational zeros test, you should first list all the rational numbers whose numerators are factors of the constant term and whose denominators are factors of the leading coefficient. I take it one more step back. I put P over Q and put a big long dividing line here and take that P, the constant coefficient, and put all the possible factors of P. And then in the denominator, all the possible factors of Q. Okay? And then put together the list of all the rational numbers that use those as numerators, those as denominators. Okay? So all the possible rational zeros are those whose factors of the constant term divided by the factors of the leading coefficient. Having formed this list of possible rational zeros, now, use trial and error to determine which, if any, are actual zeros of the polynomial. Now, it says trial and error. That sounds a bit helter-skelter. There's really an easier way than that, and the book uses it. So why do they say that? Note that when the leading coefficient is 1, then all your rational zeros are the factors of that constant term, because all you have in the denominator is 1. Okay? The possible rational zero is simply the factors of the constant term. All right, here we go. Let's go to town with the first one. All right, and they give you one just like that. Find all the rational, okay, time out before we start. Okay? Any of you want to try factoring that? Please say no. Okay? I don't know how to. If that was a 4-term polynomial, it would have hope, because you might be able to do factor by grouping, or any even number of terms. Odd number, I don't have a clue of how to go about factoring that. So, how are we going to find those zeros if we can't factor? Well, rational zeros test, give it the possible rational zero. Let me get my pen set up. Possible rational zeros will be of the form of what? P over Q, where P is all, second? Okay. All the possible factors of the constant term. And what are those possible factors? What will go into 6? Plus or minus 1. Count that one. Another. Oh, come on, you know some. What? Plus or minus 2. Another. Plus or minus 3. And another. Plus or minus 6. That's all she wrote. Okay? And the leading coefficient is 1. So the denominator is plus or minus 1. That's all she wrote there. Okay? Still, this is a lot of possible zeros, isn't it? 2, 4, 6, 8. Okay? So let's go on and list them out. We don't need to put over 1. Okay? So it's just going to be plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Okay. Now, here's sort of, in a little way, where the trial and error begins. The easiest one of these, which do you think would be the easiest to test? Probably 1, and that's exactly it. Positive 1. And here's why it's so easy to test. If you put f of 1, what would that be? 1.
To the fourth.
Yeah, and 1 to the 4th is? 1, okay. Minus 1, plus 1, minus what? Minus 3, minus 6, right? It's just the coefficients. If you put 1 in for the x's, it's just going to be the coefficients. So that's a pretty easy one to do. Let's see what we get. There's a minus 6, a minus 3, a minus 1. That's minus 10 plus 2. That ain't going to be 0. Okay? Sorry, the easiest one didn't work. Okay? But it's worth a shot. Okay? We're going to use those later. Hang on to them. In fact, right away. The next one, minus 1, I think that's the next easiest one. So let's try that one. Okay? Now, we could plug it in just like we did, but now you got to worry about the sign changes and stuff like that. I tend to make errors with sign changes. Okay, you probably don't, but I do. Okay, so what's another way? If you are testing a possible 0, what could you use? 2 sections ago, synthetic division. And what do you put inside the house? Coefficients, and there they are right up there, aren't they? So I told you we're going to use them again. 1, minus 1, 1, minus 3, minus 6. Now, the only difference is, if you're missing a term here, you didn't care up here, okay? Just checking up 1. Now you do care. 4, 3, 2, 1, 0, blast off. We got it, okay? All of them are there. How many? 1, 2, 3, 4, 5. 1 less than this? Yes. I mean, 1 more than that? Yes. We know we got them all. Okay? And then what do we do next? Skip a line, draw a line. Don't forget my little rule. Okay? And then bring down the 1. Okay? Tell me what to do next. Negative 1. Next. Yeah, I'm sorry. I interrupted you. Negative 1 times 1 is negative 1. Okay? Next. Negative 2, okay, right? Next, 2, next, 3, next, negative 3, next, negative 6, next, 6, next, ding, 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 we have a winner, okay? Because the remainder is 0, we know that's a 0, and x plus 1 would be a factor, right? Yes, we have a 0. Whoa, get out of there. Okay, so x equal negative 1 is a factor, is a 0. We found one rational 0. Now, what do we do next? Keep going. With what? Not yet. Because remember, you could have multiple zeros. So we try negative 1 again. No reason to try 1 again. It didn't work here. It's not going to work here. But try negative 1 again. See if that is a multiple 0. I sometimes forget to do that, and I usually pay for it. Because the only ones I forget to do it on are those that have them. Okay, so what do you do? Tell me. Okay, 1. Okay. Negative 1. Negative 3, 3, 6, negative 6, look at that. We have another winner, okay? And that's negative 1 again. Did I do it wrong? Huh? Oh, no, you're right, you're right. I was so eager to have a winner, I didn't have one. Okay, that's a negative 12. I should have left the thing there. But guess what? Negative 12 is not a 0. So this is not going to work. So forget that one, okay? Now we follow Ryan's advice and go with 2, okay? That seems the next easiest one to do, isn't it? So let's try 2. I left the 1 down there. That's always going to be there. So next is Next is 2, 0, 0, 3, 6. That time we do have a 0. Ding, ding, ding. Okay, we have another 0. X equal 2. Now, if that was a factor, it'd be x minus 2 is the factor. The 0 would be x equal whatever that is out there. What do we do now? Any ideas? Oh, synthetic division was so long ago, wasn't it? Whenever you get 3 down here, stop! Because what does that represent? What do those represent? The coefficients of your remainder, not remainder, your quotient. And that is a x squared plus 3. Whenever you've got a quadratic, stop. You can use quadratic formula there, or factor if you can. But what do you know about that? Is that going to factor? Is that going to have any zeros? No real zeros, okay? It's going to be 2 complex zeros, imaginary zeros, okay? That would have x equal 3, square root of 3 times I. I did it the way I said, or minus. I like to put I root 3, okay? Just because I don't like to have the I after the radical. Okay. Either way you want to write it. These are the last 2 zeros. Remember, fundamental theorem of algebra said that we'll have 4 zeros, okay? 1, 2, 3, 4, okay? Now, the other thing, as long as these are integral coefficients, actually real coefficients, then if you do have any complex numbers, they're always going to show up in pairs. No apples, just pairs. Okay, so, and here we have it. Once you get to the 3 terms here in the quotient, you can deal with that. Now, like I said before, I'm going to try not to give you any with imaginary numbers, okay? But they gave you one, so I wanted to work this out. Oh, y'all let me do this. That was example 3. That was on page 154. They skipped example 2. Shame on them. Okay? So, let's go back and do example 2. Any questions on this before we leave it? Then I'll come back and show you how they did example 3. All right, so let's go back and do example 2 first. Okay, sorry about that. Find, if possible, the rational zeros of this. Alpha of x equal x cubed plus x plus 1. Where would you begin? Well, you do your p over q. Rational zeros. And what's your p? Plus or minus 1 from the constant term, and what's your q? Plus or minus 1 from the leading coefficient. So guess what? The only possible rational zero we have. What you said. Plus or minus 1. You were psychotic. Something. Okay. You could see that coming. Okay. That's the only possible rational zero. And guess what? 1's easy. Let's try it. What would that be? 1 plus 1 plus. That's not going to be a 0, is it? So the only possible one would be negative 1. So let's do that with what technique? Synthetic division. What do we put next? The what? Coefficients. Yeah, okay. And what are they? 1. What are we missing? Oh. What do we put there? 0. Continue. 1, and 1. Okay. Remember, you have to have one more number here than you have exponent here, maximum exponent, degree. You have to have 4. So if you've done 1, 1, 1, look at that and say, oh, that's not right. Where are we missing a term? Skip a line, draw a line. What do you get? 1, next. Negative 1, next. Negative 1, next. 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 Negative 2, next. Negative 1, no good. Guess what? This one has no rational zeros. Okay? Now guess what we know about it though? It has to have a 0. Why do I say that with such confidence? What kind of function is it? It's a cubic function, meaning the degree is odd degrees are either like this or like this. You have M behavior, remember? And this one, since the leading coefficient is positive, it's like this. So guess what? Starting down there very negative and ending up here very positive, and it's a smooth continuous function, it's got to cross the x-axis somewhere. So it will have a 0, it will not be a rational 0. My guess, some irrational number. Okay? Irrational numbers don't have to show up in conjugate pairs. Sometimes they do, but they don't have to. Complex numbers with imaginary pieces to them, they, as long as these coefficients are rational or integers, I think even real, they have to show up in conjugate pairs. But irrational numbers don't. Quite often they do, but they don't in this case. Okay, so that one has no rational zeros. And that's all you had to find out. Find, if possible, the rational zeros. There were none. Okay. Now let's go back to example 3, and let's see how they did it. Okay? Because the leading coefficient is 1, they just skipped a step. They skipped the p over q, and they went to possible rational zeros of the factors of the constant term, which are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. We got there, but I wanted you to get used to doing the p over q. Okay? And you said it anyway. All right? So we try. The first one. Oh, look at that. Isn't this a shame? They say by applying synthetic division successively, you can determine this, okay? They didn't show you how you did it. Actually, the first one, the plus 1, just plug it in, okay? And you found out that wasn't a 0. Then we did negative 1, plugged it in, found out it was a 0, and then they didn't show you, but you use negative 1 again, show it's not a 0, go to 2, find out it is. Stop when you get 3 in your quotient. See, that's your remainder. That's why I like to separate it. The book doesn't. I like to separate that out so you realize that's your remainder. This is your quotient. That represents a quadratic. And here is the factor. And I really like the factor of doing this. Okay? Because, remember, the factors are x plus 1, x minus 2, and then this is a factor. That factor is irreducible. That factor cannot be factored. It does not have real solutions, only complex solutions, imaginary solutions. So therefore, that. So you can factor this completely. That's the complete factorization. It's not the complete list of zeros. The zeros would be negative 1, 2, and then your complexes. Okay. So when it does ask you to factor, if you get to 1, that when you do your quadratic formula, you obviously can't factor something like that. When you use the quadratic formula and you come out with imaginary pieces to it, then stop there and just say, that's your last factor. Okay? Irreducible quadratic. They're not saying that yet. They're going to say it later. But because the factor x squared plus 3 produces no real zeros, you can conclude that x equal minus 1 and x equal positive 2. Why in the world they put such a scrunched up x-axis there, I don't know. Spread out the y's, but they scrunched up the... Oh, no, they put those in pairs too. Okay. Those are the only two real zeros, and here's the graph that indicates that. The other two zeros are complex or imaginary, have imaginary pieces to them. Okay, see how that works? Good deal. Now, when the leading coefficient of the polynomial is not 1, okay, the list of the possible rational zeros can increase dramatically, because now that other one had 8. If you had one more factor down there, then you'd have had 16. 2 more factors, oh, it just keeps growing, okay. In such cases, the search can be shortened in several ways. Use a programmable calculator to speed up the calculations. If you got a programmable calculator, it'll probably find the zeros for you, so I mean, duh. Okay. A graph drawn either by hand or with a graphing utility. If you have a graphing utility, it will usually find the zeros for you, okay? So another duh. But you can graph it either by hand or with a graphing zero, and at least figure out where approximately those zeros are, and then pick those that would be most likely from your ratios. Or the intermediate value theorem, along with a table generated by a graphing utility. See, everything here has some type of electronic aid to it, which are fine to use. But if you don't have them, then you use the rational zeros test, just like we've been doing. Okay? And the ones you'll have are simple enough you can do this with. Or synthetic division can be used to test the possible rational zeros. Finally, well, they were doing it, but finally they get around to telling you that. Finding the first zero is often the most difficult part. After that, the search is simplified by working with lower degree polynomials obtained with synthetic division, as we did back in example 3. Recall that, this is another reminder, if x equal a is a 0, then x equal a is a solution of the polynomial equation f of x equals 0. And that's why it's just the a that goes outside there, not minus a. X minus a would be the factor, then it's the opposite of that. But, you know, when you have a solution or a 0, it is that value. Okay. Now, they're skipping example 4, example 5, before they get to this. So let's us back up. All right, and do example 4 here. Okay. Find the rational zeros of f of x is equal to 2x cubed plus 3x squared minus 8x plus 3. Okay? What would be your next step? Yeah, I had a line there, and then it disappeared, didn't it? Okay. So again, P over Q, all your possible rational zeros, your possible rational zero, whatever, will be of the form P over Q, where P is what? All the possible factors of 2, which are? Wait, 3 you said, okay. All the possible factors of 3, which are? Plus or minus 1 and plus or minus 3. That's not too many. I'd have my line way too long. And your Q would be all the possible factors of, which are plus or minus 1 and plus or minus 2. Okay, now their suggestion is list them now with this. Now, here's what I like to do. The book probably does it differently. I like to list those integers first. So I'll do the numerators all over 1, which are, just like before, plus or minus 1 and plus or minus 3. Okay? Then I start using the other denominator. And what would those be? Plus or minus 1 over 2, right? You see it? 1/2, and the other would be plus or minus 3/2. I'll put those off to the very end if I can, okay? Because the fractions just a little bit messier doing the synthetic division. And what will I try first? 1. So let's do f of 1. I like to do it right up here. You can do it anywhere. What would that be? 2 plus 3 minus 8 plus 6, plus 3. I'm doing my adding in my head already. Okay. And what does that give you? Say again? Try it one more time. Your positives are 2, 3, and 3. Those add to be 8. Minus 8 is 0. Ding, ding, ding. We have a winner already. X equal 1 is a 0. Okay? Now, guess what you got to do anyway? Synthetic division. But finding the 0 is easier that way, but you still got to do synthetic division with that 1 so you can find the rest of your factors. Okay? So what you put inside the house? Say again? 2, 3, negative 8, 3. Is that enough numbers? Yes, one more than your degree. You got it. There were no missing terms there. And then what do you do? Don't forget to skip line, draw line. Then bring down the 2. Tell me what to do next. 2, 5, 5, negative 3, negative 3, 0. We're not surprised, are we? You knew that was going to be a remainder. But what does that give you? A quadratic. Okay, there it is. So no reason to do any more synthetic division. Just do this. What is that quadratic? 2x squared plus 5x minus 3. And you set that equal to 0. And what do you do next? Okay, she wants to go straight for the quadratic formula. She doesn't want to mess around with trial and error on factoring, right? That's fine. Let's do quadratic formula. X is equal to, you tell me. Negative what? Isn't it 5? Is that what you said? It's the b. Right, yeah, negative b. Minus b. Minus 5 plus or minus. What's next? The square root of, which is, no, it's 5 squared, but that's the same thing. 25. Now I'm going to write them out. Minus 4 times what? 2 times what? Negative 3. Okay. Here's why I wanted to write it out. All over 4. 2 times a, which is 2 times 2 is 4. Okay. Get out of there. Okay. Minus 5 plus or minus the square root of 25. Now, when I do this next part, here's where I begin. I begin by counting my minus signs. That's always a minus 4. Okay? And you got one more minus. That's 2 minuses. That's an even number, so this is going to be a plus. Okay. As soon as you see it's a plus, you know you've got real zeros. Okay? We don't know what they are yet, but we know they got to be real. If that was a minus, everything depends on what that next number is. If it's greater than 25, it's complex. If it's less than 25, it's real. Okay. So what do these multiply to be? Say again? 24. Oh, and I think I can even do that. Okay. It's positive 24, right? Yeah. Okay. Over 4. Okay. And what will that be? Minus 5 plus or minus the square root of, what's 25 plus 24? 49. Hey, nice. Okay. What's nice about that? It's a perfect square. So this is going to be 5, or minus 5, sorry. I forgot it that time. Plus or minus, what is it the perfect square of? 7 divided by 4. Okay? Well, minus 5 plus 7 would be, say again, 2 over 4 is 1/2. There's a 0. Okay? And minus 5 minus 7 would be minus 12 over 4 would be negative 3. There's another 0, minus 3. Okay? Do we have enough? We have them all. Okay, my minus sign did not show up. It was there, and then it disappeared. Okay, now, let's do a quick look back. Okay? Remember our possible rational zeros? 1, we had that one. 3, we have, or negative 3, we have that one. And positive 1/2, we have that. They were all possibilities. We came out with one of each. Okay? So, shows you why it's easy. Good to start with the easy ones. The harder ones will then pan out by themselves. Now, the fact that these turned out to be rational zeros rather than irrational or complex means you could have really factored that. And it's fine. Quadratic formula is just as good as factoring. May take a little bit longer, but it's pretty certain to give you the result. If you have a lot of trial and errors here, that could take longer. But that would factor as, now I can look at the numbers and note 2x minus 1 times x plus 3. That would work, I think. Try it and see. But that's because I could look at the answer and say, I know the factors have to be x minus 1/2 and x plus 3. So that would be 2x minus 1 times x plus 3. Okay. How'd they do in the book? X equal 1, x equal 1/2, and x equal minus 3. Good for them. I'm so proud of them. Okay. They did it by factoring. You could do it by quadratic formula just as well. Oh, and by the way, every one of these examples in the book has a checkpoint following it. I was advising a student yesterday who has had Math 112 and 113, and he was talking about something, sort of complaining about the book. I said, yeah, I understand that. You know. I said, but the one thing I like about this book is this. And I showed him, and he said, what are those? I showed him the 3 websites. They're on the cover, right there. Larson Pre-Calculus, CalcChat, CalcView. He said, what are they? I said, wait. Look, okay. I showed him, I said, every one of these problems, examples in the book, says, list another one similar to it, and it gives you a free website to go to, and you can check. He said, I never knew that. And I said, in some of the examples, like, no, there's not one coming up real soon, some of the examples say you can go to this website to see a interactive version of how you solve this. And I said, and then when you get to your homework exercises, look at that. See CalcChat.com for tutorial help and worked out solutions for that. He said, I didn't know that. I said, what? Okay. And I said, and these that have the QR codes and then the red letter numbers for them, those are all at CalcView.com. I said, you can either use your phone to do the QR code, or you can just go to CalcView.com and you can see those worked out. What? All this time I haven't known. So, your instructor. Okay. He wasn't in my class anyway. All right. That was example 4. They also don't do example 5. Any questions on this before I erase it? Everybody got it? Okay. Let's go to example 5. Use the same space here. Find all the real solutions to minus 10 x cubed plus 15x squared plus 16x minus 12 equals 0. Okay, find all the real solutions to that. Okay? Now this is where that last line or so on the previous slides that we did said this, that not only do you find zeros of polynomial, you also find the zeros of a polynomial equation when it's set equal to 0. And that's what we're doing here. All right, where would you begin? P over Q. Now, wait. Actually, where I begin, when I see these complicated looking polynomial coefficients like this, I say, please, let me find the factor. Well, this is 2 times 5. This is 3 times 5. Hey, potential. Oops. That's 2 times 2 times 2 times 2. No. Not going to be able to find any common. So I can't get rid of something. So, what do you do next? You said P over Q. And what is your P? All your possible factors of, what do you say? Negative 12. And what are some of those? Plus or minus 1 always. Plus or minus 2. Plus or minus, yuck. It must be Friday. Okay. Now my eraser's not working. Okay. Plus or minus 2. Real simple stuff. Okay. Next. Plus or minus 3. Plus or minus 4. You're getting tired, are you? Okay, next. Plus or minus 6. Or plus or positive or negative 12. My word, we're going to be here all day. Okay. What was the possibilities in the denominator? Plus or minus 1. Plus or minus 2. Plus positive or negative what? 5. And plus or minus 10. Okay, that's a lot, folks. Now don't get too wiped out about it, because you look at this and say, that could be 1, 2, 3, 4, 5, 6 times 2 is 12, 24, 48. Yo! It's just getting so many so fast. Don't sweat it. You're not going to need them all, I hope. Okay. Let's list them then. What do I like to list first? The integers over plus or minus 1. So those are simply plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. Okay. Now, let's go with those with fractional forms. Tell me what they would be. You did each of these over plus or minus 1. Now I'll do each of them over plus or minus 2. First one. Plus or minus 1/2, right? 1 over 2 is 1/2. How about the next one? 2 over 2 is 1. We already listed that. Don't bother listing it again. Okay? Then, second, 3 over 2 plus or minus 3 over 2. Let's hope we don't have to go that far. Next one. Second, which is 2. We've already listed that. Next, 6 over 2, which is? We've already listed that. And next is? 12 over 2, which is 6. We've already listed that. See, it's not quite as many as you thought it was. Now, I want to remind you of something, okay? Remember when we first started this, to use the rational zero test back on page 153, you should first list all the rational numbers whose numerators are factors of the constant. Wait. Trying to find it. Oh, here it is. Where P and Q have no common factors other than 1. So you see we're getting rid of those that have the common factors. The 12 and the 10 have common factors, so that's why we're able to eliminate those. Okay, so next. Then we do all these over 5. So that would be plus or minus 1/5, plus or minus 2/5. No relief here. Plus or minus 3/5. Plus or minus 4/5. Ooh, we still got a plenty, don't we? Next. Plus or minus 6/5. Ooh, and let's start it over. Plus or minus, second, 12/5, 12/5. Okay. Well, not a lot of relief there. But now let's go to the last one. Okay. That was our 5. Let's do the 10. What would those be? Plus or minus 1/10. Plus or minus, what would be next? 2/10 would be 1/5. We've already got that one. So, finally a little relief. Next, 3/10. Next, 4/10 would be 2/5. We already got that. 6/10 would be 3/5. We already got that. 12/10 would be 6/5. We've already got that. That's enough, though. Okay, I don't want any more than that. We could be here all day. Okay, hopefully not. Okay. Now, so what would you do first? Yeah, let's do 1. And what will f of 1 be? Even though we're not listing it as that. What would it be if you plugged in 1? What would that be? 10, negative 10 plus 15 plus 16 minus 12. And what does that equal? Second? It's not 0. That's the sad news. It's positive 31 minus 22, not 0. But it didn't hurt to do that. All that it does is eliminate the plus 1. Okay, so that's out of there. What you want to try next? Negative 1. Let's try that one. Okay, what do you put inside the house? Negative 10. Oh, wait, I put a comma there. I don't need a comma. I don't know why. Oh, I've been putting so many commas, that's why I did it. Okay. Okay. All right. Then 15. Then 16. Then negative 12. We just have them listed up there. Is that enough numbers? Yes, because the maximum exponent is 3. We got 4 numbers, we're fine. Then we skip a line, draw a line, and do what? Bring down the negative 10, and then positive 10. That gives us 25. Ooh, this isn't looking good, is it? And then we get negative 25, and that gives us negative 9, and that's not going to work, is it? No. So we can stop there. Shucks. Negative 1 didn't do us any good either. So erase the negative 1, erase the 25, this 10, that minus 25, and that minus 9. It erased my line 2. It wasn't supposed to do that. Put that back. What do you want to try next? 2. Okay. What do you get next? Negative 20. Yeah. All right. Negative 5. Negative 10. 6. Second. 12. 0. Ding, ding, ding. We did get a winner. And guess what else we got? A quadratic at the bottom. Yes. So we know that, and this one was asking for what? Find all real solutions. Here's one solution. X equal 2. There's a solution for that equation we had at the beginning. All right, now what do we do? Negative 10, what'd you say? X squared minus 5x plus 6 equals 0. Okay, you know that's got to be, if there are any more solutions, there'll be solutions of that. Now, how do you want to go with that? Okay, I knew Rachel would want to use a quadratic formula. So how does that go? X equal 5 plus or minus the square root of 25 minus 4 times negative 10 times 6 all over negative 20. 2 times a. Okay. So I'm going to proceed with this to go 5 plus or minus the square root of 25. And what do I do next? Plus, exactly. You have two minuses, so that's a plus. Plus what? 240, is that what you said?
I was doing that, yeah.
Oh, okay. 4 times 6 is 24 times 10 is 240. Oh my goodness. What have we got? Well, anytime you have that big a coefficient, you're going to have some big numbers involved. Okay? That's why synthetic division is so nice. Okay? You can get some big numbers, but you're just adding and multiplying. So you don't have to. Okay, so what does this give us? That gives us a 5 plus or minus the square root of what? 265, is that what you said? 265. I don't, goodness gracious. All right, this is driving me nuts. The pen will write and then disappear and over negative 20. Now, did you already pull on your calculator to see if 265 is a perfect square? It's not, is it? Okay. Now, I need more room. Let's go up to the top and see if we can mess up there for a while. This will be 5 plus or minus. Now let's see if we can find any perfect squares hiding in 265. I know nothing with a 2, none whatsoever. Okay. I was hoping something with a 5 in it might do. Okay, I know 25 wrong. Now, you may be right. Okay? Yep, you're all right. There are none. So, our last two last two solutions to this are, you got x equal 2. You got x equals 5 plus the square root of 265 over 20, over minus 20, and x equal 5 minus the square root of 265 over a minus 20. Now, frankly, just between you and me, I really don't like having the negatives in the denominator. They're perfectly correct. So I think I would have written this way. I'm going to erase something here so I can write it the way I would write it. You don't have to do this just because I say I like it this way. Let me get these out of the way so I have some room to write. It just, to me, looks and feels a little neater. Okay? All right. Those last two, I would have pulled the minus up here and say x equal minus 5 plus square root of 265 over 20. That, to me, just looks neater than having the minus in the denominator. Now the other one, I would have done this way. Pull the minus up there and then minus 5 plus root 265 over 20. Okay. That's just me. Okay. The answers they have are perfectly correct. And you can approximate the answers. They did. The square root of 265 is a fairly large number, but it's an irrational number. Add 5 to it and then divide that sum by negative 20. And then when you do the minus, you do the same thing. Only that turns out minus in the numerator, minus in the denominator, so that gives you a positive number. And there is a checkpoint. Okay. You just got to go?
Yes, sir. I don't want to be late to my meeting.
What's that?
I don't want to be late to my meeting.
Right, understood. Well, y'all feel okay with just calling it quits here? Okay. I thought I had a meeting today too, and then I found out it was canceled. All right. So I'll be here working the rest of the afternoon, rest of the morning.
Thank you, sir.
All right. Thanks for coming. Appreciate it. I think we got a lot covered. We'll pick up with conjugate pairs next time. I hate that people miss this. This is a pretty important one, so I hope they'll be listening to it on YouTube. What's that? I can't hear it, sorry.
It's a long section.
Yeah, it is. It is a very long section. Oh, I didn't get homework exercises. I'm glad I hadn't turned off YouTube. You could do any of the odds, 9 through 13. They're all at Calc Chat. 9's at Calc View. See, I say this every time. Either 15 or 17. They're both at Calc Chat. Any of the odds 19 to 27, they're all at Calc Chat. 25's at Calc View. And one like we just did, either 29 or 31, they're both at Calc Chat. 29's at Calc View. Let's go on and do either 33 or 35. They're both at Calc Chat. And 37 or 39. They're both at Calc Chat. Okay. We will stop there because this conjugate pairs only deals with complex numbers, parts with imaginary components. So you're not going to be responsible for that. I'll go over the slides with it, but we'll go right on to factoring a polynomial. So, not a bad place to stop. And not too bad a time. Didn't get basically got about an hour in, rather than an hour and 15 minutes. So thanks again for being here.